Alright, so part B asks us to determine the time it takes to stop. We're just going to use a kinematic relationship for constant acceleration. We know that this travels, the constant acceleration here is A. We know what the direction of that is going to be, and we know what the displacement is for this as well. So we can plug in our values for 0 meters per second squared. The initial velocity here is 25 meters per second squared, plus 2 times the acceleration, which we're going to calculate, times this displacement, which is 62.5 meters. We can plug in the values here, and I'm just going to leave these constants the way they are. We'd subtract 25 squared from both sides. This is 25 meters per second squared divided by 2 times 625 meters. Oops, I forgot to put my units in. It should be meters per second. Let's put those in there. And that's going to be equal to A. And here again we see actually that, oops, there we go. We see that this is going to give us a negative value, right? That's a negative for acceleration. We chose to the right to be positive, so this negative is actually an important thing. That's just kind of reinforcing the fact that this acceleration is pointing to the left. Alright? So we can figure out what the final value of that is, and I won't take the time to record that, but we can figure out what that is. We could plug this in at some point, and then we can use our relationship about the displacement of x times the initial velocity times time plus 1/2 times this acceleration up here times time squared. We know what the displacement is, we know what the initial velocity is, and we know what the acceleration is, and we can then solve this quadratic for time. Alright? We can plug that value in there. And then, again, it asks us what is the mass of this. Now, the part C is what is the mass? What is the mass? We already wrote down the Newton's second law for this that showed the net force acting on this particle is equal to the particle's mass times its acceleration. And here in part B we actually solve for the acceleration. Well, we have a value for the acceleration that hasn't been computed yet, and so we can actually figure out what the mass is by plugging it in. We were told in the initial problem that the net force acting on it is 12 or 15 newtons, and that equals its mass times its acceleration, and the acceleration is this crazy value here that we already wrote down, which was minus 25 meters per second squared over 2 times 62.5 meters. And looking at this, I can already see that I made a mistake in writing down what the net force is, because the net force has a particular direction. So this acceleration had a negative value because it was pointing, whoops, to the left. Sorry, probably seen some of that. So our net force is also pointing to the left, because this is something, the acceleration is to the left, the net force is in the same direction, so we also should be putting a negative value here. And so when we divide through by this value, 15 newtons by this value here, we'll get a mass that's going to be some positive value. And then we can plug that through and figure out what that number is.